In this video, we're going to begin our discussion of volumes of revolution, and we're going to start with what are called the disk and washer methods. So the disk method involves something like we're going to see here. If a region in the plane is revolved about a line, the resulting solid is called a solid of revolution. So let's consider the region bounded by y equals f of x, shown in yellow, and the x-axis from x equals a to x equals b. We're going to revolve that region about the x-axis. So if you can imagine that, we're going to get something that is going to look, trying to make this look three-dimensional here. So we are going to get something that's going to look like that. I'm not sure how you would describe that, but it's not hollow in the inside, it's a complete solid. So to do that, we're going to look at our differential slice. So we'll look at our rectangle. So look in 2D for a moment here. We're going to take that rectangle and then we're going to spin it around the x-axis there. When we do that, what we're going to see is this really thin cylinder. So I'm going to pull it out and I'm going to lay it flat, even though it's actually going to be vertical when we see it in the picture. But I'm going to turn it around and lay it flat, so it's going to look something like that. So that's going to be like a mini cylinder. And we're going to call that cylinder a disk. So this we are going to refer to as a disk. Now, because it's a mini cylinder, its volume is going to be pi r squared h. And so in our case, this radius right here is coming from right here. So that is our function. So that's going to be our function squared. And the height of our cylinder is this little distance here, which we are going to call a delta x. Now, in general, this is going to be part of a grander, larger scheme. Any of these slices that we're going to look at in different contexts are going to be the area of the cross-sectional piece times delta x, or sometimes a delta y if we revolve it around a vertical line. So in this case, our pi r squared is going to look like that, pi f of x squared delta x, and so our volume then would be adding up the volume of those slices. So we can pull the constant pi outside, we would integrate from a to b, and we would get our function, in this case f of x squared, and that delta x would become dx. So that's going to be our general rule. So the takeaway, what we want to know is for a disk that our differential slice is going to be pi r squared h. Again, that's the area of that circular cross-section, and the h is going to be our delta x. Okay, so let's look at an example. So here on the blue, we can see f of x is sine x, and that's supposed to be this curve here in the yellow. So that's our f of x equals, square root of sine x. And we want to find the volume of the solid form by revolving that region about the x-axis from 0 to pi. If you want to see what this looks like on your graphing calculator, you can choose the 0 and pi to be the x-min and x-max, and the 0 and the 1 to be our y-min and y-max. So our delta volume, again, we're going to imagine taking this rectangle, and if we spin it around the x-axis, we're going to get something that's going to look, I don't know if that's very understandable. I'm going to slide it out, turn it around, and so it's going to be a very thin cylinder, what we're going to refer to as a disk. Our delta volume is going to be pi r squared h, which in our case, because that little thickness there is going to be a delta x, this is going to be a pi r squared delta x. The radius of our disk is going to be this distance right here, which is our function, which is going to be the square root of sine x squared. let me put that equal sign. Let me do that. So our radius is going to be pi, and we're going to get our square root of sine x, that's our function, squared times a delta x. So our volume is going to be pi, and we will go the integral from 0 to pi, and that's going to be a sine squared x and then a dx. Okay, and we'll just set up that integral. I'm sorry, it's the square root of sine x squared is going to be just sine x. So this integral we can do fairly painlessly. That's going to be the integral of sine x is going to be a negative cosine x. We've got the pi in front, and we're going to evaluate that from 0 to pi. So that's going to be a negative pi times the cosine of pi minus a negative pi times the cosine of 0. Since the cosine of pi is negative 1, that'll make that pi plus, and since the cosine of 0 is 1, that will also be pi, and that will make our volume 2 pi. Let's look at another example. So here we have in the yellow this y equals e to the negative x. We're going to go from 0 to 1, and we're going to revolve this also around the x-axis. So our little differential rectangle, when we spin that around the x-axis, is again going to give us a little thin cylinder, which we're going to call a disk. And our delta volume for a disk is going to be pi r squared h, which for us, that h, that little thickness, is going to be our delta x. So the radius is going to be our function again. So that's going to be pi times, we're going to get e to the negative x squared times a delta x. So remember, when you raise a power to a power, we're going to multiply those exponents. So that's going to become e to the negative 2x. So our volume is going to be pi, and our integral will be e to the negative 2x dx. We'll make a u substitution where u is the negative 2x, the du will be a negative 2 dx, and the dx will be a du over negative 2. So this is going to become, I should get the limits. We're going to go from 0 to 1. So that's going to be integral. I'm going to forget the limits for a minute. We're going to go e to the u, and that takes care of our e to the negative 2x. The dx, we're going to put in a du over negative 2, and so that's going to be a negative 1/2 integral of e to the u du. I'm going to come over here, that's going to be a negative 1/2 e to the u, which is our negative 2x, and we're going to evaluate that from our x limits of 0 to 1. So that's going to be a negative 1/2 e to the negative 2 minus a negative 1/2 e to the 0. So that's going to be a 1/2 e to the 0 is just 1/2 minus, and we can either leave it as a 1/2 e to the negative 2, or if you wanted, we could call it 1/2 minus and then put that e squared in the denominator. So either of those is equally acceptable for our volume. Let's revolve the region bounded by y equals square root of x, the y-axis now. So we're going to now use our y-axis as a boundary, and y equals 2, which is going to come through here, and we're going to revolve that about the y-axis. So now what we want to do is draw our rectangles horizontally, since we're going around the y-axis. Now we can see that our delta volume is going to be pi r squared h. This time we're going to get that h, that little thickness for our cylinder, is going, our little disk, this little thickness is a delta y. Now that has significance. That means we want our radius to be, it has to be a function in terms of y. So we're going to have to rewrite our y equals square root of x as x equals y squared. So that's going to make our radius y squared be squared, and then there's our delta y. So our delta volume is going to be that pi y to the fourth delta y. Now we're going to need y limits here, since we're going to integrate using these slices going horizontally. And so we can see that we're going to go from 0 to 2. So our volume is going to be, the pi is going to come out. We'll go 0 to 2, those are y limits, of y to the fourth dy. So that's going to be pi times, and the integral of y to the fourth is going to be y to the fifth over 5, and we're going to evaluate that from 0 to 2. So 2 to the fifth is 32, so that's going to be 32 pi over 5, and then minus 0 is going to make that be our volume. Okay, now the next one we're going to talk about is the washer method. So a washer is kind of an extension of the disk method when our integral is going to have a hole in it. So if you look at the region bounded by f of x in the yellow and g of x in the green, and we're going to do that from x equals a to x equals b, and we're going to revolve it around the x-axis. So if you look at this representative rectangle, you can see, hopefully, as we spin that around, I'm going to pull it out and then I'm going to turn it on its side. It's going to look like a cylinder with a hole in it that's also a cylinder. So the hole itself is also a cylinder. So you could think of that delta volume as pi, and then maybe the big radius squared minus the little radius squared, and then times a little delta x. What we are going to do is call this big radius the outside radius. So that's short for outside radius. And we're going to say that the smaller one, the hole, is going to be the inside radius. And so we're going to abbreviate that IR. So our delta volume is going to be pi times the outside radius squared minus the inside radius squared times a delta x. Okay, and so that's going to be our starting point. And our outside radius is going to go from the, let me pick a different color here. So we're going to go from the line of revolution, the axis of revolution, to the outer edge of the solid. So that's going to be our outer radius. And the inner radius is going to go from the line of revolution to the edge of the hole. So that is going to be our inner radius or inside radius. Let's see how it looks with an example. So we're going to take the volume of the solid that is going to revolve the region bounded by y equals square root of x and y equals x squared about the x-axis. So this is what that's going to look like. You can see they're going to intersect at 0 and also at 1. We're going to imagine we're going to take a representative rectangle. When we spin that around the x-axis, then when we pull that out and turn it on its side, it's going to look like what we're going to call a washer. So there is our washer. And a washer, we said, has a delta volume. That's going to be pi times the outside radius squared minus the inside radius squared, and in our case a delta x, because that's the thickness of that little cylinder with a hole in it, our washer. So the outside, so our delta volume is going to be pi. Now the outside radius is going to be that distance that goes from the line of revolution to the outer edge of the solid. So it's going to be that distance. Now that's a vertical rectangle, so that outer radius is going to be the top curve minus the bottom curve. So the top curve so our outer radius is going to be that top curve, which is the square root of x. And the bottom curve is really this bottom distance here, which is y equals 0. So that's going to be our outer radius. So our delta volume is going to be pi times our outside radius squared is going to be the square root of x. I'm going to write it this way for a moment, squared. Now that inside radius, I'm going to pick a different color here. I think I'll go with the green here. So our inside radius is going to go from the axis of revolution to the edge of the hole. So this distance right here is our inner radius. And that inside radius or inner radius, again, because it's vertical, we're going to go top minus bottom, but that's just going to be, again, our x squared minus 0. So that's going to be an x squared. So we're going to get a minus our x squared squared, and then a delta x. So our delta volume is going to be this pi times, and the square root of x squared is x, and minus the x squared squared is x to the fourth, and then that's going to be times the delta x. So our volume is going to be pi. We're integrating here from 0 to 1, and that's going to be x minus x to the fourth dx. So that's going to be pi times, and the integral of x is going to be 1/2 x squared, and then that's going to be a minus 1/5 x to the fifth, and fortunately we're just going to go from 0 to 1. So 1 squared is 1, that's going to make that 1/2, and minus 1 to the fifth is 1, that's going to be a 1/5, and then 0 to those powers is 0. So 1/2 minus 1/5 is going to be 5/10 minus 2/10, and I left off the pi, so let me put it back in there. And so that is going to be pi times that, so we're going to get 3 pi over 10 as our volume. Okay, so let's look at another one here. Here now we're just going to set up the integral but not work it all the way out, because the setup is the really interesting part here. And this time we're going to take the region bounded by f of x equals x squared plus 1 and the x-axis, and we're going to do a few different ones looking ahead here. So we're going to do, I guess, just 2 of them. So y equals -2 and y equals 6. So we're looking at a rectangle here. So you're going to imagine here's your rectangle, and we're going to spin this first around the line y equals -2, which is going to be down here. So as you spin that rectangle around there, you can see there's going to be a hole in it coming from this gap there. So when we look at that thing on its side, there is going to be a hole in it, and so that is going to be our washer. So we can see that this will be a washer. So our delta volume is going to be a pi outside radius squared minus inside radius squared times a delta x. So the outside radius is going to be that distance that goes from the line of revolution up to the outer edge of the hole. So this is our outside radius. So our outside radius, and because it's vertical, we're going to go top minus bottom. The top of that rectangle is on the curve, so that's going to be our x squared plus 1. Minus the bottom of that, that is the axis of revolution, that line of revolution, is that -2. And so that is going to make our outside radius be x squared plus 3. Right? You can kind of see that. This much of the radius is our function, and we're going to add another 2 to that, making the x squared plus 1 plus 2, x squared plus 3. So that's going to make our outside radius be x squared plus 3 squared. Now our inside radius is going to be that distance from the line of revolution to the edge of the hole. So that distance is going to be our inside radius. And again, that's a vertical distance, so we're going to go top minus bottom. And the top curve is just the 0, and the minus the -2 is going to make that inside radius be 2, and it's the same all the way through. So our hole is always going to be that radius of 2. So we will go then a -2 squared, and that'll be a delta x. So our integral, so our volume, and we're just going to set it up, is going to go from 0 to 2, and it's going to be that x squared plus 3 squared minus 4, and then the dx. Now, the second one, that line y equals 6, so we're up at 1, 2, 3, 4, 5 is the top of that region, so y equals 6 is going to be up here above our region. So now, again, when we spin it around there, hopefully we can see that this rectangle, looking at that same red rectangle, this time when we spin it around this way, we're going to get a hole in there, but we're going to get this kind of washer there again. So I'm going to draw it this way, and so we're going to still have a washer. And so our delta volume is still going to be pi outside radius squared minus inside radius squared times that delta x. Now in this case, the outside radius is going to go from our axis of revolution, that's right in here, to the outer edge of our solid, which is going to be this right down here on the x-axis. So that outside radius, so it's going to be top minus bottom, that's going to be 6 minus 0. So the outside radius is always going to be just that 6. So that means we're going to get pi times, whoops, let's go try that again. So pi times the outside radius squared. Now the inside radius is going to be the distance from the axis of revolution, the line of revolution, to the edge of our hole, which is going to be that distance down here to our rectangle. So this distance is going to be our inside radius. And that inside radius, again, we're going to go top minus bottom, is going to be 6 minus our function, x squared plus 1. That's going to be that y value distance right there. So that is going to be, and we can even just leave it like that because we're just setting up our integral. So our inside radius is going to be this, well, let's go ahead and distribute it. 6 minus x squared minus 1 is going to be a 5 minus x squared. So that'll be a 5 minus x squared squared delta x. So our volume is going to be pi. We're going to integrate from 0 to 2 again, and it's going to be 36 minus the 5 minus x squared squared dx. Okay? All right, very good.